Okay, welcome to 8.3. It's called Normal Sampling and Modeling. There's two parts. There's the normal sampling part, and there's the modeling part. It's modeling with for discrete data. Anyway, so let's look at part A, the normal sampling. So a lot of times you have a huge population and you only sample a little part of that. We'll talk about more of that when we get to the next unit, the single and two variable statistics. But a sample is just a small portion of the population. Population is the whole group of objects or people that you're studying, and the sample is just a smaller size. So if you take a sample from a normal population, a lot of times the distribution of frequencies in the sample data tends to follow the same bell-shaped curve as the underlying distribution for the whole population. So again, a lot of times when you collect data, this normal distribution pops up a lot. There's something called the sample mean. I gave it the letter mu before. The mu is actually the population mean. So this letter here, this mu, that's the letter that you use for the population. There's another term another variable when you're talking about the mean of a sample. You calculate it the exact same way, but you gave it a different variable name. It's x bar, right? So don't have to worry too much about that. Same thing for standard deviation. There's a standard deviation of the population, which we call sigma. Standard deviation of a sample is called S. And there's actually a slightly different formula to calculate it. We haven't really calculated. We have our calculators calculated for us, but there's actually two formulas. But let's not worry about that for now. All right. Again, the larger the sample, the more reliably a sample data will reflect the underlying population. So if you only take a few, like 5 or 6 data points, it's not really going to be reflective of the population. But if you take a 70, 100, or 200, or 1,000 data points, it's going to more represent it's more likely that it's going to represent the normal population. All right. So this is actually question 1 out of the text, out of the homework. So if we do this question, you don't have to do question 1. A police radar unit measured the speeds in kilometers per hour of 70 cars traveling along a straight stretch of highway in Ontario. The speed limit on this highway is 100 kilometers per hour. The speeds of 70 cars are listed below. Okay, so 2 questions. Calculate the mean and standard deviation of this data. This is pretty easy. We're just going to use calculators to do it. And then question B, what is the probability that a car traveling along the stretch of highway is speeding? So, to answer this question, there's a couple of steps. So I'm going to write the steps here. Anybody have a speeding ticket yet?
No.
No? Okay, that's good. I've had a few. Try to avoid it. I heard there's a lot of, with this lockdown, there's a lot more road racing because the roads are so empty. Something I heard in the news.
Yeah, they're a lot of fun.
Yeah. Oh, don't do that. Don't do that. Don't race on roads. All right. So the steps we're going to do is we're going to enter the data on a spreadsheet. Enter the data on a spreadsheet or a calculator. There's no reason to calculate the mean and the standard deviation by hand. So, and then second step, is we're going to determine the sample mean, which we call x bar. The sample standard deviation, which we're going to call S, which is the equivalent of mu. And we're also going to determine the median. All right. So, and I did it. Let's, where the heck is my sheet? I put this onto a spreadsheet. I'm not going to refer to the spreadsheet because it's not going to be part of the video, but that's all the data. And in the spreadsheet, you can sort it. So there's 70 values. And then there's a little the spreadsheet can calculate the median, calculate the mean, calculate the standard deviation, right? So let's just write that down. So the mean was 110.3. The standard deviation, the sample standard deviation was 110.68, and the median was 111. Now, this was a homework question, and I don't expect most people to do this, the step that I'm going to do now for homework, but really what I wanted to determine is, does this data, is the sample distributed normally? Like, this might be a weird sample. It might not be, we would expect the population at large to be distributed normally, but and that this should be distributed normally as well. But what if it isn't? Let's actually check to see if it is distributed normally. So step 3 was check. Is sample distributed normally? Okay, so what can you tell me about the normal distribution? What are its properties from 8.2? What are its properties? Can somebody?
The median and the mode are all the same.
Yeah, it's basically, is it symmetric? Is it symmetric? So we're not going to look at every single point, but a good way to check if it's symmetric, does mean equal median? And the answer is yes. Roughly, we have the mean is 110.3, the median is roughly 111. So yeah, we'll assume it's symmetric. What other things do we know about the normal distribution? What properties? Let's say you go from the mean and you go plus or minus 1 standard deviation. What percentage should be within 1 standard deviation? Did you guys remember? What percentage should be within 1% standard deviation of the mean? Give me a guess if you don't know.
67%.
68.
Oh, I was close enough.
You're close. What the actual is, and I actually did this. Again, the actual was 68.6. So this data, the actual was 68.6. So that's pretty close. And do you remember what plus or minus 2 standard deviations was? Want to give me a guess?
95.
95.5%. I think it's 95.5. The actual is 98.6 for this data. So, therefore, close enough. So, therefore, it's close to. It's not perfect, but it's close enough that we can use it to. Again, when you have a question like this for homework, we're just going to assume we can use the normal distribution. That we don't have to do the check. We're just going to assume. If you have to do this for every single question, it's going to take a while to do that. So you don't have to do this check. You're just going to assume that it's close to a normal distribution. All right. So part A. Calculate the mean and standard deviation of this data. Well, the spreadsheet did that for us. There's the mean and there's the standard deviation. All right, so that's already done. Let's answer B now. So part B, we'll do over here. So what's speeding? What is the probability of the car? When do you speed? Officially. What's considered speeding? It's going greater than, x is greater than 100, right, kilometers per hour. All right. So the probability that x is greater than 100 is going to equal the probability. How do we calculate probabilities again? If it's something is we're assuming it's normally distributed. So how do we do that again? Do we use x values or do we do something else?
Z values.
Z values. Z values. Z scores. So we're going to, instead of x, we're going to convert it to a z score, and the z score is going to be greater than, not 100, but how do you convert this x value to a z score? So
You
z.
have to convert 100 into a Z score.
Yeah, that's what I'm asking. So remember, a z score. What's the formula? You take the z score for an x value. You write the x value, and then you do two things to it. You subtract
The mean and divide by the standard deviation.
You guys did the homework, right? Okay. All right. Yeah. So you take the mean. The mean is the value is 100, right? You subtract the mean, and then we divide by 10.68, the standard deviation. So how did we get that? That's just the formula. All right. So equals the probability. If you do that, what do you get? What's 100 minus 110.3 divided by 10.68? I'll just write the answer. It's 0.96. All right. So there's kind of something kind of tricky when it's a greater than and not a less than. What do you have to do if it's a greater than?
You have to do 1 minus the complement.
Yeah. Because the z scores are always less than. So it's 1 minus the complement, the probability of z being less than minus 0.96 equals 1 minus, and how do we look that up? Here's the chart. Minus 0.96, right? So going over to column 6, it's 0.1685. And that is 80. I'm going to convert it to a decimal percent because I like percents. Right. So the probability of somebody speeding is 83.2% if we base it on this data, this sample. It's not the whole population, but it's a sample of the population. Now, there is a much easier way to get an answer. What's a much easier? I mean, this is the way we expect you to do it, in this unit. But what would be an easy way to get the? Let's do. Anybody think of another way? So the method 2, the probability of speeding is going to be. Well, how do we calculate probability normally? When we did counting, right? It's the number of ways you can speed over the total ways, right? So what's the number? The number of ways you can speed is the number of cars speeding. Number of cars speeding over the total number of cars, right? Isn't that what we learned in probability? Right? So let's just do that. How many cars here are speeding? How many of them are going greater than 100? So anything 101 and greater. Does anybody want to just guess to me, just by looking at it, how many you would get? There's 70 altogether. Give me a number. How many of them are greater than 100 out of the 70? Nobody wants to guess?
60.
56. Right. So that equals 80%. So, this is a lot easier than this. But this is if you do the statistical method and try to, assuming that that's a normal distribution, this is your answer. The answer is that the reason that it's not exactly the same because it's not exactly a normal distribution. It's close, right? So otherwise these two should be pretty even closer, but they're pretty close. Okay, we're good. So how do use sample data to create probabilities. You just assume that the sample data is normally distributed and you can calculate your probabilities. Do I have to leave this on the, if you're copying it down, are you guys all copied up now, or can I move on?
Yep.
I can move on. Okay. So, the second part of this chapter is something called modeling discrete data using the normal distribution. The normal distribution is not for discrete data, it's for what? Not for discrete data, but for, begins with a C. Continuous data. So we're going to use the normal distribution to model discrete data, but it's not quite the same, because by definition the normal is for continuous data. All right. So, discrete data can sometimes be modeled by a normal distribution. To do that, we have to do something called continuity correction, which is treating discrete values as though they were continuous. And I'll explain that in a second. And it should be used to calculate.
No, this is like calc stuff.
Oh, you do this in calc?
It's just the word continuous.
It sounds like calc.
Okay, yeah, okay. All right. Don't worry, it's not that bad. This is easier. This is not too bad. We're going to use this procedure to calculate probabilities. This will be explained in the example below. Here's an example of using continuity correction, which I haven't explained yet, when modeling discrete data with the normal distribution. A company, and this is the exact example from the textbook, okay? It wasn't too creative. I didn't create my own. So, a company produces boxes of candy-coated chocolate pieces. The number of pieces in each box is assumed to be normally distributed with a mean of 48 pieces. There's supposed to be 48 pieces of chocolate in the box. But there's a standard deviation of 4.3 pieces. Quality control will reject any box with fewer than 44 pieces, and boxes with 55 or more pieces will result in excess costs to the company. Alright, so everyone, pretend you're a manager of a chocolate manufacturing company, and you're making these boxes of chocolates, and you have some data, and you want to answer this question: what is the probability that a box selected at random contains exactly 50 pieces? So, if this was a normal distribution, what's the probability of getting exactly 50? Remember, in a continuous distribution, the answer for one specific data point is 0. So you can't use, it always has to be a range. So we're going to treat discrete data as continuous data. And this is called continuity correction. Alright, so exactly 50 pieces. We can't use exactly 50. Now, we always have to do a range. What do you suggest the range should be to get 50 pieces? Because we can't use 50 because the probability of 50 exactly is 0. So we got to use a range. So what can we model 50 as?
To 55.
No, that's too big, because then you would get 46 pieces, 47, 48, 49, 50.
Could we do like 49 to like 51?
But that would be 49, 50, and 51. We just want 50.
Oh wow. Oh, like decimals.
Yes. Can you give that to me?
Like 49.9?
Oh no, 0.9. What about 49.8?
49.8.
What about 49.7? So, give me the most logical range to model 50 with. That
I have no clue.
You don't want to get any answers that include 49 or any answers that include 51. You want some, like, if you were rounding numbers, what would you round to 50? What numbers would you round to 50?
49.5.
49.5 to...
Like 51.4?
51.4. No.
Or 50.4, sorry.
Yeah, but let's do 50.5 because we're going to do less. We're going to do more than 49.5 and less than 50.5. Does that make sense?
Yes.
Okay. Therefore, we're going to the probability that X, number of chocolates, we should probably say that X represents the number of chocolates, is greater than 49.5. So instead of putting X equals 50, we're going to write X is greater than 49.5 and less than 50.5. That's the same thing. Because there's no other way to do it. So that's going to equal the probability. Again, we want to convert these probabilities to z-scores, right? Right? What's the z-score for this one? The 49. What's the z-score for 49.5? So it's always, remember, z-score equals the mean minus the x value minus the mean over standard deviation. Right? So the x value is 49.5 minus the mean. What's the mean here? The mean is right there, right? And there's the standard deviation. So minus 48 over 4.3. And then on the other side, on the 50.5, you're doing the exact same thing, but just going to replace the 49.5 with the 50.5. All right, that equals the probability of that number, and save some time. That number is going to be 0.35, and you can just round it to 2 decimals because the z-score tables are only 2 decimals. So just don't give me like 10 decimals. Round it to 2 decimal places, and on the other side, this guy goes down to 0. Oh, sorry, this was 5/8. Sorry, this was 5/8. Wait a second. No. Sorry. Take that back. Take that back. It was 0.35. And this is 0.58. Right. But how do you do this? How do you handle a range? How do to use the z-scores? How do you do this? How do I get the range between 2 values? Well, you find the probability of the top one. All right, and then you subtract the probability of it being, below 0.35. Right? You guys did this in the 8.2 homework. Okay, so if you look that up, again, how do you look that up? 0.58, 0.58, 7190, 0.35, 0.6368. Therefore, 82. We have to use continuity correction to be able to do this calculation. But 8.2% of the time, you get exactly 50 pieces. All right. Does that make sense? This is an example. Again, this is discrete data. The number of chocolates is only integer values. It's not, you don't get decimals, so this is the only way we can get around it. All right. What percent of the production will be rejected by quality control as containing too few pieces? So what's too few? up here in the question, what is too few? Quality control will reject any box with fewer than 44 pieces. So this is less than 44. Right? Okay, so again, so we're going to accept 44 pieces, right? And we are going to reject 43 pieces and anything lower than 43. Right? So if we use continuity correction, we're going to accept any value that is what? So if you had a histogram, I don't know. If this was 42, 42, 43, 44 pieces, whatever, right? Remember, we're going to approximate this with a continuous thing. This is a histogram with discrete data. We want anything 44 or above, right? Containing too few. So we're looking at we're looking at the ones that are contained too few. So it's actually the other way. We're looking at anything less than 44. Right? So we start there, anything less. So what's our definition of having too few? Using continuity correction. It's actually, let's just zoom in a little bit here. Where is this point? There's 43, there's 44. This is halfway between 43 and 44. So where is that point? So too few officially is going to be 43 and a half, right? Too few is less than. Using continuity correction, we're going to accept any value greater than 43 and a half. So too few is going to be any value less than 43 and a half, right? Does that make sense? I hear it's very quiet there. I don't know if I'm doing this by myself or if there's anybody else there, but so we're going to use continuity correction for exact values, and also for ranges. We're going to go. We're going to use it every single time. So too few is going to be officially anything less than 43 and a half. So the probability of x being less than 43 and a half is the same as the probability of z being less than what? Because we don't have charts on x, we don't have charts on z. So this is going to be, can somebody give me the values here? So whatever the x value is, and then we have to do two things, right? Just like we did up here, we subtract the mean, and we divide it by the standard deviation. Right. So if you change that to a number, it's minus 1.05, minus 1.05, minus 1.05, right there, I guess, 0.1469. Therefore, if you convert that to a decimal, 14.7% will have too few. Not a very good factory when 15% of your packages are not good. So quality control is not the greatest in this plant. There's one last question. Are we good there? Okay, one last question. Each filling machine produced 130,000 boxes per shift. How many of these will lie within the acceptable range? So what is acceptable again? If you look at the question, what's acceptable? What are you going to accept?
Bigger than 43.5.
Yeah, well, without doing continuity correction, it was 44 to what? On the low side, and
55.
so 55 is too much, but 54 is okay. So 44 to 54. So 43 is too few, and 45 is too many. All right. So again, whenever we're doing discrete data, we have to do continuity correction. So that's not what we're going to use as our range. We're going to use what? So is it going to be 44 and a half or 43 and a half? Like this is going to change to a half. This is going to change to a half. So what's the lowest number that rounds to 44? Is that what you should think? All right. So it doesn't go up to 44 and a half. It goes down to 43 and a half. Right. What's the lowest number that rounds to 44? And then here, what's the highest number that rounds to 54? Typically you would round, like you wouldn't say 54 and a half, you would say 54.499999, but we're just going to round it to a half, halfway between 54 and 55. Does that make sense? All right, so probability of x being between 43 and a half to 54 and a half is the same as the probability of z scores being between the z-score equivalent of this and the z-score equivalent of that. So the z-score equivalent of this would be 43.5 minus 48 over 4.3. This one would be 54.5 minus 48 over 4.3. And that's going to be minus 1.05. Alright, so then, again, when we have a range, you have to find the probability of z being less than this, subtract the probability of z being less than that. So you don't have to write all these steps. If you want to just, skip it, not write that, but just go right to this line, that's fine. Probability of this is 0.9345. Trust me, you can check the table if you want, but I think I did it right. The probability using the Z table is 0.1469. The answer is 0.788. Therefore, 78.8% of the time the boxes are acceptable. But is that what the question's asking? No, it says, if you made 130 boxes, how many of those will be acceptable? So there's one further step then, right? So what the heck is 78.8% of 130 boxes? That's a lot of boxes. So out of 130 boxes, 78.8% of them, or 102, if you round it to the nearest thousand, 102 boxes but overall, this is in a modern plant that's not acceptable. It should be 99.9% of your boxes are acceptable, and not 78.8. So anyway, that's the lesson. There's some homework. We've already done question 1. Question 1 was the first example. So I haven't done the homework. I will do it myself and post the answers, but I'm going to call it, I'm going to finish the lesson right now. Let's see what the time is. Stop, hold on. How do I stop it now?